we can easily calculate the coordination number of the central metal atom and which is given in the coordination complexes. While naming this coordination compound, always use a small letter, and please see that whether it is anionic complexes or cationic complexes, and always writing the oxidation state of the central metal atom, use the Roman numbers. So especially if it is an anionic complexes, the central metal atom should be end with ATE. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called coordination compounds. Under that, we have discussed about the classification of inorganic salt. Under that, we have discussed about the simple salt, double salt, and also with the complex salt. And also, we have learned about the differences between double salts with the complex salts, and also we have learned the important definitions which has been involved in coordination compound. So today we will move on to the next topic of this unit by understanding coordination sphere. So we are going to understand what? Coordination sphere, which is the last terminology which is there in the coordination compound. Okay, and later on we are going to discuss with the coordination polyhedron, and we are going to discuss about the oxidation number calculation in the central metal atom. So how to calculate the oxidation number in the coordination compound, that we are going to understand in this session, and we are going to understand the tables of some of the common ligands which we are using in the coordination compound. At the last, we are going to understand the nomenclature of the coordination compound. So let us see what is a coordination sphere. So already we have understood that coordination sphere, which is nothing but a bracket which used to represent the coordination complexes, or you can say that it is a sphere that used to represent the complex. Is it right? Yes. The central metal ion and the ligand attached to it are enclosed in a square bracket which is known as what? Coordination sphere. So it includes what? Central ion as well as with the ligands. So the ligand as well as with the central ions will be get enclosed in a square bracket. That bracket itself we call it as a coordination sphere. For example, the complex name is potassium hexacyanide 4. So in this you can see that this is a coordination sphere which is enclosed between the ligand. Is it right? So Cn is my ligand that encloses the central ion along with the ligand. Hence it is known as what? Coordination sphere. And you can see that this is Fe. It is nothing but another element which are involved in that complexes, and this potassium is a counter ion. You can see that. So Fe is a central atom and Cn is my what? Ligand, and K4 it is nothing but a counter ion which is a potassium ion which act like a central ion. You can see here the central ion as well as with the ligands, they are enclosed by a square bracket. So this square bracket always encloses a central ion along with the ligand. Hence it is known as what? Coordination sphere. So hope you all understood with the coordination sphere. Next we will see density. So density is defined as number of coordinating atom present per ligand. Here you can see that in this complexes, you can see that what is the density? So there are 6 coordinating ligands will be there. So it is hexacyanide. Is it right? So why it is hexa? Because there are 6 coordinating ligands which are present along with the central ion as well as with the counter ion. Okay, that is known as what? Density. So what does the density indicates? Which indicates the number of coordinating ligand or coordinating atom per ligand or present in the ligand. Okay. Next we will see what is coordination polyhedron. The spatial arrangement of the ligand which are directly attached to the central metal atoms of the ion, which is known as what? Coordination polyhedron. Here you can see that I have represents the different coordination complexes where you can see that the central metal atom are directly bonded to what? Ligands. This spatial arrangement of ligands towards the central metal atom, the spatial arrangement we call it as a coordination polyhedron. You can see that in first example, there is a one central metal atom surrounded by 6 ligands. Is it right? So this is known as octahedral complexes. Similarly, you can see that we have one more central metal atom surrounded by 4 different or 4 coordinating ligand. Hence, the complexes will be tetrahedral. Similarly, if central metal atom is 1 and surrounded by 4 different ligands, then it gains a square planar structure. Similarly, you can see that in this structure, central metal atom is 1 and it is coordinated by 5 ligands. Hence, this structure will be trigonal bipyramidal structure. Similarly, you can see that the central metal atom surrounded by 5 different coordinating ligands and it acquired the square pyramidal structure. This is how, based upon the number of ligating atom forms a coordination compound with the central metal atom, we can arrange this a spatial structure in the space that is said to be coordination polyhedron. So, hope you all understood with the coordination polyhedron. Now, let us see how to calculate the oxidation number in the coordination complex. Okay. In that, specially we are going to understand the calculation of coordination number in the central metal atom. Okay. So, what is the coordination number? So, the coordination number of a central metal atom in a complex is defined as the charge will be carried if all the ligands are removed along with the electron pair that are shared with the central metal atom. So, what is the coordination number? Coordination number which tells us about the charges which is there in the central metal atom even though when you are removing the ligands. Okay. Let us see how to calculate the coordination number of the central metal atom. First, I will go with this one. This is hexacyano-copper-take 3 minus. Is it right? In that, how to calculate the coordination number of the central metal atom? We know that this is a central metal atom and this is a 4 ligands. 4 CN ligand. So, how to calculate this? Now, I will take note that example Cu CN4 coordinations via 3 minus. So, I will consider copper as X plus 4 into 1 because the coordination number of the CN is 1 is equal to minus 3. So, X plus 4 is equal to minus 3 and X is equal to 4 minus 3 which is nothing but a 1. So, the coordination number of the copper in this complex is 1. This is how we can easily calculate the coordination number of the central metal atom and which is given in the coordination complexes. We will discuss with another 2 examples so that you will understand how to calculate the coordination number of the central metal atom. I will go with this complex. I will take the cobalt as a X which is a central metal atom. You can see that it has been coordinated with the 2 different kinds of ligand. Is it right? It will be amino and this is water and again we have a chlorine. How to calculate this? I will take a note this as X plus 4 into the oxidation state of or oxidation number of the ammonia is 0 plus for the water is also 0. For the chlorine it is 1 into minus 1, which is equal to what? Plus 2. So, x plus 0 into anything, it is 0, plus 0 into minus 1, which is equal to 2. So, x is equal to 2. If you taken out the 1 outside, it will become 1. So, x is equal to plus 3. So in this complexes, you can see that the cobalt has got plus 3 oxidation state. So, in this example, you can see that cobalt is the central metal atom which has been coordinated with the two different kinds of ligand. One is ammonia and one is chlorine. And how to calculate the coordination number of this complex? I will consider cobalt as x plus 4 into 0 plus 2 into minus 1, because for the chlorine it is minus 1 and for the sulfate it is plus 2. Okay. Next, x plus 4 into 0 it is 0, 2 into 1 it is minus 2, which is equal to 2. Similarly, I can write this as plus into minus, it is minus. So, x will be equal to 2. If the 2 comes outside, will become plus 2 and it carries how much? So, oxidation state of cobalt in this complex is plus 4. Okay. This is how we can easily understand the calculation of the oxidation number of the central metal atom which is there in the coordination complex. So, we learn more about this coordination number while doing the nomenclature of the coordination complexes. Okay. Next, we have homoleptic complexes and heteroleptic complexes. Again, for the examination point of view, especially for the 2 marks, it is very important to know about homoleptic and heteroleptic complexes. So, here the word itself says that homo means same. Is it right? Yes. The complexes in which central metal atoms are bounded by only one kind of ligands, then we say it as homoleptic complexes. Here you can see that in this example, the cobalt is a central metal atom surrounded by 6 ammonia, and all these ammonia are the same ligand. Is it right? And the structure will be goes like this. So, this is a central metal atom surrounded by how many ligands? 6 same kind of ligand, that is ammonia. Is it right? NH3, NH3, NH3 and NH3, and it has how many charges? Plus 3 charges. You can see here the central metal atoms are bounded by same kind of ligands. Such complexes are said to be homoleptic complexes. We have one more complexes known as heteroleptic complexes. In this, we can easily understand that central metal atoms are bonded by more than one type of ligands. You can take the example of CNH3 4 times Cl2. I can write the structure here. So, the cobalt which has been donated by or coordinated by 4 ammonia ligand, and you can see that we have another one kind of ligand known as chlorine, and it carries what? Plus charge. You can see here the central metal atoms are coordinated by 2 types of ligand. One is ammonia and one is chlorine. This is how, if the central metal atoms are bonded by same kind of ligand, we say it is what? Homoleptic complexes. If the central metal atoms are bonded by more than one different kinds of ligand, we say it is heteroleptic complexes. Okay. So, more about this, we are also going to understand while doing the nomenclature. You will see different kinds of homoleptic as well as heteroleptic complexes. Now, let us see some of the common ligands and their charges. Okay. It is very important to know this, a ligand with the charges while doing the nomenclature. Ma'am, whether we need to learn all these complexes? Not necessarily, but while doing the nomenclature of few complexes, you must know this, a ligands with the charges. But for your competitive examination, it is very important to know the charges of the ligands. Okay. First, I'll take only with the monodentate ligand. Already we have learned that even though the monodentate ligand which forms a single coordination bond with the central metal atom, it will be out of three types. It will be neutral monodentate ligand or positive monodentate ligand or negative monodentate ligand. Is it right? Yes. I'll go with the first one, that is neutral monodentate ligand. Here I have examples. You can see that NH3 we call it as ammonia, but in coordination compound we call it as amine. We call it as what? Amine, and their wordings also different. We write AMMINE. Okay, and it carries how many charges? 0 charges. Okay. Next we have water. We say it is aqua and it carries what? 0 charges. Similarly, we have carbonyl, that is CO. We call it as carbonyl and it carries what? 0 charges. Similarly, the NO, which is known as nitrosyl, and it carries 0 charges. Similarly, we have pyridine and it is represented as PYR and it carries 0 charges. So, we can easily remember the example of amine, aqua as well as with the carbonyl and nitrosyl groups which are carrying the 0 charges. Okay. Next, I'll go with a monodentate ligand which carries the negative charges. So, here you can see that N3 which is azido, the Br which is bromido which carries -1 charge. Similarly, the Cl which is known as what? Chlorido, and Cn which is known as cyanido, and the F which is fluorido, and OH which is hydroxido, and ONO minus. In this, you can see that this is again NO2, but the oxygen is a ligating ligand. Is that right? Hence, it is known as nitrato oxygen. But in this example, you can see that even though it is NO2, the nitrogen itself is a ligating ligand here. Hence, it is named as nitrato N. So, these two things you must know that while doing the nomenclature. See that which ligand is ligating towards the central metal atom. If it is an oxygen, we say it is nitrato oxygen or nitrato O. If it is a nitrogen, we say that it is nitrato nitrogen, that is N. Okay. And you can see that the one thing is when we are dealing with this monodentate ligand, especially with the anionic ligands, it always ends with IDO. You can see that it always ends with what? IDO. You can see that cyanido, fluorido, hydroxido, bromido, azido. So, anionic ligands are always end with what? IDO. Okay. Next, we have few more anionic ligand. You can see that NO3 nitrato, CH3 COO minus which is acetato, and SCN which carries negative charge which is thiocyanato, and NCN which is isothiocyanato. You can see here again, even though it is same, but sulfur is a ligating ligand towards the central metal atom. Here, the nitrogen is a ligating ligand which ligated towards the central metal atom. If it is in sulfur, we say it is thiocyanato which carries how many charges? Negative charges. Negative means -1. Okay. Similarly, you can see that nitrogen is a ligating ligand which ligate towards the central metal atom. Hence, it is named as isothiocyanato. Okay. It carries negative charge. Hence, it is an example for anionic ligand. We'll go with the cationic ligands here. So, it carries the +1 charge. You can see here NO plus which is nitrosonium, NO2 plus which is nitronium, and NH2, NH3 which is hydrazinium. you can see that the cationic ligands are always end with IUM. Always end with IUM, whereas anionic ligands are end with IDO. Okay, always remember the anionic ligands. Anionic ligands are end with -1. Similarly, the cationic ligands are end with IUM. Okay. Next, we have bidentate ligand. In that are of two types. In the bidentate ligands which carries neutral charges, we have two examples. That is bipyridine, which is known as bipyridine, which carries 0 charges, and we represent En for ethane 1,2 diamine. So you will use that En, which is a short term, while doing the nomenclature as well as by understanding the isomers. You will see that what does En represent. En represents what? Ethane 1,2 diamine, and the structure will be like this: CH2, NH2, CH2 and NH2. Okay, it is ethane 1,2 diamine. And since we have one more bidentate ligand which carries -2 charges. Okay, so you can see that CO3 2, which is carbonato, and O2, which is oxido, C2O4, which is oxalato, and SO4 2, which is a sulfato. Okay, so this is how we can easily remember the ligands and their charges. Okay, especially go with the mono and bidentate ligand. Next, we have some of the rules to name the coordination complexes. Okay, so in your second PUC, you must worry only about nomenclature of mononuclear coordination complexes. So only the mononuclear coordination complex will be given to you. You have to apply the rule and you have to name the coordination complexes. Okay, we'll see what is the rule says that the cations will be named first, both positively and negatively charged coordination entity. If cations are given as a ligand, if it is carries negative charges or positive charges in their outermost of the coordination sphere, it has to be named first. Okay, that is the first rule. And second rule says that ligands are named in an alphabetical order. Suppose if the coordination complex is consists of both amino and chlorido. Okay, first we have to name with the amino as a first ligand, followed by chlorido, because while naming these ligands in a heterolytic complexes, we have understood that more than 2 kinds of ligands can coordinate it towards the center metal atom. In such cases, while naming such ligands, we have to go with the alphabetical order. Okay. Next, the names of the anionic ligands will be always ends in O, and those in case of neutral and cationic ligands are always ends with same. We have some of the exceptional cases. You can see that the aqua, water, and amine for NH3 and carbonyl for the CO and nitrosyl for NO, because these are the monodentate ligand which carries the what? 0 charges. And the rule 4 says that to indicate the number of individual ligands, the prefixes will be used. Like di, tri will be used, and if the prefixes are present in the names of the ligand, then the terms such as bis, tris and tetrakis will be used. Here you can see that this is a nickel is a central metal atom, followed by 2 chlorine ligand and also by 2 pH3 ligand. In such cases, while naming this ligand, you can see that there are 2 pH3 groups will be there, and we use the name as dichloro bis triphenyl phosphine nickel 2. So while naming these ligands also, if number of ligands are more and more with the same ligands, we'll go with the di as well as with the tri as well as with the tetra or with the tri also. But if the prefixes of the ligands are also increased by its number, then we use bis, tris and tetrakis like that. Okay. Next, the coordination state of the central metal atoms are indicated by what? Roman numbers. Here you can see that after naming this complex, I have used the coordination number of the central metal atom by writing in terms of what? Roman numbers. So it is very important to know that while writing this complexes, always use the Roman number to indicate the coordination number of the central metal atom. Then we have a last rule that says that if the complex's ion is cation, then the metal name should be used first. Okay. So if the complexes which consists of cation, okay, then in such cases, the metal name will be named first. For example, the complex cation will be called as iron and platinum will be called as platinum, etc. You will see all these rules while doing the nomenclature by taking some of the examples. Okay. And the last rule says that if the complex ion is an anion, metal name will be used with the suffix known as ate at the ending. For example, CO in the complex anion, you can see that it is tetra-thiocyanate cobaltate and the oxidation state of that cobalt. Okay. So, especially if it is an anionic complexes, the central metal atom should be end with ATE. If it is an cation, we have to use the first metal name. Okay. Next, the neutral complex molecule is named as complex cation. So, here I have represents a few examples. You can see that in this, it is named, this is a central metal atom surrounded by 3 different kinds of ligand and it should be goes in order. So, it is diamine, chlorido, nitrido, N, because N is a ligating ligand towards the central metal atom, and the oxidation state of platinum we have to calculate. Okay. You can see here, this is an example for the complex which consists of 3 different kinds of ligand. Hence, it is an example for heteroleptic complexes. You can see that the platinum with oxidation number will be calculated like this. I'll taken out the platinum as X. So, X into X plus 2 into 0 for ammonia because it is a neutral ligand. For the chlorine, so it is 1 into minus 1 plus for nitrito again it is 1. So, 1 is equal to 0. So, X plus minus 1 plus 1 is equal to 0. So, now you can say that X is equal to 1 plus 1 which is equal to 2. So, oxidation state of the platinum in this complexes is plus 2. So, in this example again, potassium is a central metal atom. How to calculate this? So, I will take 3 into X you can say because 3 potassium ions will be there. For the chromium, so it is 0 plus for the oxalator we have understood that it carries minus 2 into 3 is equal to 0. So, 3x is equal to minus 6. 3x plus minus 6 is equal to 0 and 3x minus 6 is equal to 0. 3x is equal to 6. X is equal to 6 minus 3 which is equal to 3. So, in this example you can say that the potassium which is having plus 3 oxidation state. Similarly, you can go with one more example and it is named as dichlorido ethane diamine which is known as EN. That is ethane 1,2 diamine cobalt, and oxidation state of cobalt is 3 chloride. Okay. Next we have cobalt is a central metal atom surrounded by 2 different kinds of ligand, and it is named as pentamino carbonyl cobalt 3 chloride. Similarly, you can go with this example where the central metal atom is again cobalt surrounded by the counter ion also, and it is named as mercury tetrathiocyanato cobalt tate. Why it should be 8? Because we have understood that if it is an anionic complexes, always the ending word should be end with ate. Similarly, we will go with this example. This is tetracarbonyl nickel 0, because it is an example for neutral ligand when it does not carry any charges and the charges will be 0. Next we have triamino triaqua cobalt 3 chloride. Okay. Next we have, this is a cationic complexes and the names will be goes like this: potassium tetrahydroxido zincate 2. Why it should be end with ate? Because it is an example for anionic complexes. Okay. So hope you understood with this example. Again we will discuss with a few more examples so that you will understand how to name the coordination complexes. I'll go with the first one, and this is an example for the heterolytic complexes, and first I'll go with this ligand, and chromium is my central metal atom, and first I'll go with the calculation of oxidation number of the chromium. I'll consider X plus 3 into 0 plus 3 into 0 plus 3 into minus 1, which is equal to 0. Then X plus minus 3 is equal to 0, and it carries plus 3 charges. Chromium has plus 3 oxidation state, and the name will be goes like this. It is triamine triaqua chromium 3 chloride. Chromium 3 chloride. You can see that while naming all these elements or the ligand along the central metal atom, I have not used any capital letter. This is the one thing that you should keep it in your mind. While naming this coordination compound, always use a small letter, and please see that whether it is anionic complexes or cationic complexes, and always writing the oxidation state of the central metal atom, use the Roman numbers. Okay. Next, I'll go with this example. So, platinum is my central metal atom. I'll go with the first oxidation number calculation. So, for the platinum, I'll consider X plus 5 into 0 plus 1 into minus 1. For again bromine, it is minus 1 plus 3 into minus 1, which is equal to 0. Then X minus 1 minus 3, which is equal to 0, and X, which is equal to 4. So, what is the oxidation state of the platinum here? 4, and it will be named as pentamino chlorido platinum 4 bromide. Platinum 4 bromide. Okay. Next, we'll see with this example now. So, again, this is an example for the cationic complexes. We have to start the naming of these complexes by taking the name of the central metal atom first. So, I'll go with the first calculation. So, 4 into X plus 0 plus 6 into minus 1, which is equal to 0. So, 4x plus minus 6 which is equal to 0 and 4x is equal to 6 and x is equal to 6 minus 4 and which is equal to 2. So the oxidation state of the potassium is 2. And how to write this complexes? First we have to use a metal name and it will be named as potassium hexacyanido. So iron it is, right? So the potassium hexacyanido ferrate. We use the iron as a ferrate here. What is the oxidation state? It is +2. Okay. So it is potassium hexacyanido ferrate 2. Okay. We have one more example. So the naming will be goes like this. It is a counter ion. I'll go with the naming now. For this complexes, you can easily say that it is an example for the zero monodentate ligand, which indicates that it is a neutral ligand. I'll go with the calculation part. So 2 into x plus for the nickel it is 0 plus 4 into minus 1 which is equal to 0. So 2x which is equal to 4 and x is equal to 4 minus 2 which is a 2. And it is represented as sodium tetrachlorido nickelate 2. You can see that while naming this the cationic complexes, always it should be end with ATE. Okay. Next, we have some of the example for the cationic complexes. We'll see how to name this complexes. And the coordination number calculation, I'll go with the first one. So for the cobalt, we need to calculate here. So x plus 6 into 0 plus 3 into minus 1 which is equal to 0 and x minus 3 which is equal to 0 and it carries what? Plus 3 oxidation state for the cobalt. And it is named as hexamine cobalt 3 chloride. Okay. Next, we'll go with the oxidation number calculation with the platinum. So it is x plus 4 into 0 plus 2 into minus 1 which is equal to plus 2 and x minus 2 which is equal to 2 and x is equal to 4. So what is the oxidation number of the platinum? It is plus 4 and it is named as tetramine chlorido, that is dichlorido. Why it is di? Because 2 chlorine atom will be there. Platinum, what is the oxidation state? 4, platinum 4 ion. Okay. We'll discuss with another one example. This is a chromium is a central metal atom. So it will be x plus 4 into 0 plus 2 into minus 1 plus minus 1 which is equal to 0. So x minus 2 minus 1 which is equal to 0 and x is equal to 3. So oxidation state of the chromium will be plus 3 and it is named as, it is tetra aqua dichlorido chromium 3 chloride. Chromium 3 chloride. Okay. This is how we will name this compound, and you can see that while naming this coordination compound, I have not given any space in between them. Okay, this is how some of the things you need to keep it in your mind while doing the nomenclature. So we have one more example here. The iron is a sentimental atom. Okay, so how to calculate the oxidation state for the iron? So it is X plus 5 into 0. For the thiocyanate, we know that it carries -1, and we know that SO2 will carry +2. Is it right? So it is X minus 1 plus 2 is equal to 0 and X is equal to 3. So oxidation state of the iron will be +3. So and it is named as penta-aqua thiocyanate iron 3 sulfate. Iron 3 sulfate. Okay. So this is 4 different examples for the cationic complexes. Okay. Next we'll see with some of the neutral complexes also, and calculations of this all neutral ligands will be goes like this. So it is X plus 4 into 0 is equal to 0. So X is equal to 0 and it is named as tetracarbonyl nickel 0. Tetracarbonyl nickel 0. So in this example, the platinum is a central metal atom. I'll consider X plus 2 into 0 plus 4 into -1 which is equal to 0. X minus 4 which is equal to 0 and X is equal to +4. Okay. And how to name this? It is named as diamino tetrachlorido platinum 4. Diamino tetrachlorido platinum 4. Okay, this is how we also name the neutral ligand. We have anionic complexes examples also. We'll see with how to name these complexes. Always remember, when you're naming this anionic complexes, always name the metal first. Okay. So how to start here? You can see here how to calculate the oxidation number. So it is 3 into X plus for the cobalt it is 0 plus 6 into for the nitrito it is -1 which is equal to 0. 3x minus 6 is equal to 0 and x is equal to 6 minus 3 which is nothing but a +3 oxidation state, and it is named as potassium hexanitrato. You can see that oxygen is a ligating ligand. Oxygen cobaltate 3. Next we have platinum, and their oxidation state will be X plus 6 into -1 which is equal to -2, X minus 6 which is equal to -2, and X is equal to -2 plus 6 which will be 4. Okay. So it will be usually named as hexachlorido platinum 4 ion. Okay. Next we have one more complexes. Here you can see that the sodium is a central metal atom. So X plus 0 plus 4 into, for the OH it is minus 1. So it is equal to 0. So X is equal to minus 4, which is equal to 0. X is equal to plus 4. And it is named as sodium tetrahydrazine aluminium 4. Tetrahydrazine aluminate 4. Aluminate 4. Next, we have one more complexes. Again, you can calculate the oxidation number. 2 into X plus 0 plus 4 into minus 1, which is equal to 0. 2x minus 4, which is equal to 0, and x is equal to 4 minus 2, which is equal to plus 2. Okay, and it is named as potassium tetracyanidor cuprate or cuprate, you can say cuprate 2. Cuprate 2. Okay. In all this example, I have used the ATE to end with metal atom. Okay. So this is how we will name the anionic complexes, cationic complexes, as well as with the neutral ligands or with the neutral complexes. So hope you have understood with all this example I have discussed. We also discussed the nomenclature of the coordination compound. If the name has been given, how to write the formula. So how to write the formula of the coordination complex if the name has been given. For that also we have a certain rule. We'll see that what is the rule says first. So first, what is the rule says? The central metal atom is listed first. It is the first rule. And ligands are listed in a alphabetical order. So that polydentate ligands are also listed in alphabetical order. In case of abbreviated ligand, the first letter of the abbreviation will be used for determining the position of the ligands in that coordination sphere. And also, the formula of the entire coordination entity is enclosed in square bracket, and the ligand abbreviations and the formulas of the polyatomic ligands are enclosed by parentheses. Already I have explained that rule also. And there should be no space between the ligands and with the metal within the coordination sphere. For the charged coordination entity, the charge will be indicated outside of the square bracket. So as we have indicated that platinum CO42 minus, so the charge should be indicated outside of the coordination sphere. And the charge of the cation is balanced by charge on the anions. These are the certain rules we also use if the name which has been given, how to write for the formula. So I have listed out the names of the coordination compound. We'll see how to write the formula now. So I have tetamine aqua chlorido cobalt 3 chloride. We know that cobalt is my central metal atom, surrounded by what? 4 amine group and also with 1 water and 1 chloride group. So that is why I have written cobalt NH3 4 times, water with a chlorine as well as with a chloride anions. Okay. Next, the potassium tetrahydroxidozincate. Here the potassium is a central metal atom surrounded by what? Hydroxido means OH group. How many will be there? Tetra means 4. OH group will be there surrounded by zinc. So it is potassium tetrahydroxidozincate. Zincate 2. Next is potassium trioxalato-aluminate 3. So here again potassium is my central metal atom surrounded by 3 oxalate ligand and also with aluminium. Next we have dichloro-bis-ethane 1,2 diamine cobalt 3. You can see that this is my central metal atom which is surrounded by 2 two different kinds of ligand, which is ethane 1,2 diamine. So I have used bis ethane 1,2 diamine dichlorido. Okay, so it is dichlorido bis 1,2 diamine cobalt 3. Okay, next we have tetracarbonyl nickel. So this is the example for the neutral complexes where the nickel will carry the 0 charges. Nickel is my central metal atom surrounded by 4 different carbonyl groups as a ligand. Next we have tetramino diaqua cobalt 3 chloride. So cobalt is my central metal atom surrounded by what? Tetramino means 4 amine group and diaqua means 2 water molecule along with CH3 groups. So this is an example for what? Tetramino diaqua cobalt 3 chloride. And we have one more example, that is potassium tetracyanonickelate 2. Here the potassium is a counter ion surrounded by 4 Cn, that is tetracyano, and this is my central metal atom, that is a nickel. We have one more example, tris ethane 1,2 diamine chromium 3 chloride. Chromium is a central metal atom surrounded by 3 En, that is ethene 1,2 diamine and also with 3 chlorine atoms. Okay, that is chloride. Next, amine chlorido nitrato N platinum 2. Here you can see that the platinum is my central metal atom surrounded by 4 different kinds of ligand. Is it right? One is amino, bromido, chlorido, nitrato. In that, nitrogen is a ligating ligand which carries +2 oxidation state. Next, we have dichlorido bis ethene 1,2 diamine platinum 4 nitrate. In this example, you can see that platinum is a central metal atom surrounded by chlorido ethane 1,2 diamine, which is a bis, and 2, that is di-nitrato complexes. Is it right? And the platinum will carry +4 oxidation state. Similarly, we have one more example, iron 3 hexacyanoferrate 2. So this is a counter ion and this is my central atom. So surrounded by 6 cyano group, okay, and also which is surrounded by what? Counter ion. So this is how, if the names which has been given, we used to write the formula of that given coordination compound. So in the next class, we are going to understand more about the isomerism and their types. Okay. By this, I like to say that what are all the things which I covered in this session. Again, it is very important for the examination point of view. Have a look on it and try to work out. We'll meet you with the next session. Till that, take care. Be safe. Thank you.